Hello and welcome to our discussion of logic where we are going to be analyzing some arguments. So how does this differ from what we've done before is now we're going to be looking at two types of arguments. The first one being inductive, where you have a specific premise or premises that leads to a general conclusion. So a typical example would be the first premise is bluebirds fly, right? And then I've seen hummingbirds fly, and I've seen cardinals fly. So my conclusion is that all birds fly, right? So you take specific things and then generalize them. That's inductive reasoning. The second type of argument is deductive reasoning, where you take general premises that lead to a specific conclusion, right? So it's kind of the opposite. You take specific, almost like specific observations or specific facts, and you try and generalize from them, and that's inductive. Deductive is you take general premises, things that are generally accepted as truths, and then see if it leads to a specific conclusion. So an example would be a premise is that all doctors are intelligent. And then your premise is, well, Dr. Jones is a doctor, and your conclusion is, therefore, Dr. Jones is intelligent. That's kind of a typical deductive reasoning argument where you have a general statement and then you have a premise where you kind of take a subset of that general statement, right? Like, so all doctors are intelligent. If we believe that to be true, and then we know that Dr. Jones is a doctor, therefore, right, Dr. Jones is in that group of doctors, then therefore Dr. Jones must be intelligent. And we'll see how Venn diagrams play out really well with deductive reasoning. Okay, so how do we evaluate these things? Well, an inductive argument does not prove its conclusion true. Right? It doesn't prove anything, so it's really only based on its strength. An argument is strong if a compelling case is made for its conclusion. So you say it's a strong argument if it seems to compel you to think that the conclusion is true, and it's weak if the conclusion is not really supported well by the premises. So here's an example. A movie director tells her producer, the person who's going to pay for the movie, hey, don't worry, the film's going to be a hit because as evidence, she cites the following facts. She's hired big stars for the lead role. She has a great advertising campaign planned, and it's a sequel to her last hit movie. All of these things should lead to, a hit movie. And so that's why she says her movie will be a hit. Now let's explain why this argument is inductive and evaluate its strength. Well, we know it's inductive because each of those three pieces of evidence are specific characteristics of her movie, right? She talks about who the lead actress will be, how her marketing will go, and that it's a sequel to her last hit. Those are all specific things. And then the conclusion is more general. It just says, and then therefore my movie will be a hit, which is just a general thing. And so that tells us the argument is inductive. And we can base its, strength or weakness on, how strongly those things really kind of influence the last thing. And we know that even, the best planned movies can be flops, that it's a pretty weak argument. A lot of sequels, everybody knows that most sequels are worse than the first movie, right? There have been plenty of movies with big name actors in them that have flopped, and there have been plenty of movies where they throw a crap ton of movie in advertising and they still flop. So it doesn't really guarantee much. Okay, how about evaluating deductive arguments? Well, we're going to apply two things to evaluate them. The first is the argument is valid if its conclusion follows necessarily from its premises, regardless of the truth of the premises or conclusion, right? So basically, if it just follows from the premises, it's a valid thing, meaning that if these premises are there, then the conclusion has to also be there. That would make it valid. In addition to that, it's sound if it is valid and the premises are true. So here's where we can kind of put them in a table and look at the key differences between the two, so it'll help you identify which is which. Right? So in inductive, we have a conclusion is formed by generalizing from a set of specific premises, whereas a deductive reasoning, we have a specific conclusion, right, is deducted or deduced from a set of more general or equally general premises. So deductive reasoning, we go from the general down to the specific, and in inductive, we go from specific out to the general. So they're kind of polar opposites. Okay, an inductive argument cannot prove its conclusion true. At best, it can just be a strong argument. And validity concerns only logical structure. A deductive argument can be valid even when its conclusion is blatantly false. So keep that in mind when we talk about validity. Even though the conclusion is false, it can still be a valid argument if it just follows kind of the rules of how you set it up. So it is valid if its conclusion follows necessarily from its premises, right? So basically, if this has to be true based on the premises, or it has to follow, not necessarily true, but it has to exist based on its premises, then it's valid. Okay, Venn diagrams are a great way to test for validity for a deductive argument. So you can draw a Venn diagram that represents all the information contained in the premises and check to see whether the Venn diagram confirms the conclusion. If it does, then the argument is valid. Otherwise, it's not valid. So like I said, the Venn diagram is the way to see if it's just a valid deductive argument, not whether or not it's true, just valid, right? So evaluate the validity and soundness of the following argument. All fish live in the water. Whales are not fish. Therefore, whales do not live in the water. So here's your Venn diagram, things that live in the water. And fish are within that circle. But then whales are not fish. Well, all we know is that whales are not in this circle. So they could be here in the blue stuff, or they could be out here, right, in the whatever color that is. And because the premises are not set up in such a way that it forces whales to be in one position or the other, this is not a valid argument. Okay? So that's how validity works. It's just whether or not everything has to be in a certain place. So because whales could be in either of these things, and we kind of stick it on the border to indicate that, this means the premises do not automatically support the conclusion. So it's not a valid argument. Okay, basic forms of conditional deductive arguments. There are 4 forms that use kind of the P's and Q's that we've done with our truth tables. And again, who cares if you know what these words are? Maybe just put them in your notes in case they come up. But affirming the hypothesis. So if P, then Q. So P is true, therefore Q is true. So basically, if we have this structure that if P, then Q, and we know P is true, then therefore Q is true, that's a valid argument. But however, if we're trying to affirm the conclusion, right, so the hypothesis, and we say if P, then Q, and we say Q is true, therefore P is true, that's invalid. Because remember from our truth tables that if we have an if-then statement and Q could be true without P being true, right? So that's an invalid argument. And then denying the hypothesis. If P, then Q, says P is not true, therefore Q is not true, also invalid. We've seen that again from our truth tables. So then denying the conclusion, if P, then Q, and then we say Q is not true, then that forces P to not be true. That is valid. So the only 2 valid if-thens that we saw this in the truth tables is a true P leading to a true Q is a true statement, and a false P and a false Q comes when it comes backwards. If we have a false Q, then we know P has to be true, right? So that backwards is kind of the contrapositive. Okay, so affirming the hypothesis, consider the following argument. Premise. if a person lives in Chicago, then the person likes windy days. So that's our first if-then, right? So P is the person living in Chicago. Q is they like windy days. So, right? So if P, then Q. Then Carlos lives in Chicago. So P is true. So conclusion, Carlos likes windy days. Now, according to the structure, right, we have if P then Q, P is true, then Q. That's a valid argument. It's a valid argument. Now, is it true? Do we know that Carlos likes windy days? Heck no, right? So again, remember, these things are not valid or invalid because they're true statements. They're valid or invalid based on their formatting, right? How they're put together. So this is a valid argument, even though it leads to a possibly false statement, because we honestly have no idea if Carlos likes windy days or not. How about affirming the hypothesis? Use a Venn diagram test to show that the argument concerning Carlos and Chicago is valid, right? So here's the first premise is if P then Q, in which P is the person, right, lives in Chicago, Q is the person likes windy days. So that's what we said before. So here's windy days, here's lives in Chicago. So basically we're saying if someone lives in Chicago, right, if someone is from Chicago, then they like windy days. So that's what an if-then looks like with a Venn diagram, that it has to be a circle inside of a circle. Because if you're in this circle, you must also be inside this circle. That's what an if-then means. And then we say, well, Carlos lives in Chicago, so Carlos has to be put in this circle, right? The X. Remember, we can't put the X in different places. So once we know the X has to go in one spot, we know it's going to be a valid argument, and therefore it's a valid argument. So this is just talking more about how we know it's a valid argument because we put the X in that spot, right? In the conclusion, we've already talked about this, so you can read those on your own. And then how about if we try this with affirming the conclusion? So the premise, if an employee is regularly late, then the employee will be fired. So you can see that regularly late is within the fired circle. So the if then, the P is always inside the Q in that case when we're doing if thens. Now, Sharon was fired. Okay. Well, if Sharon was fired, that just means that X is somewhere in the big blue circle. It could be out here in the blue circle that's not in the regularly late, or it could be in the regularly late, right? So again, we're stuck with this premise that puts our decisions on a borderline. And so the conclusion that she was regularly late is an invalid argument. Again, it could be true. Maybe she was regularly late. Could be false. Maybe she wasn't regularly late. Does not matter. The truth or untruthness, right, of the argument is not what we're checking. It's the validity of the argument, and this is an invalid argument. All right. So this just walks us through why it's invalid, which we've talked about. Okay, how about example 5, denying the hypothesis? Again, we can use a Venn diagram to test this one. The premise is, if you liked the book, then you'll love the movie. Premise is, you did not like the book. Conclusion, you will not like the movie. So let's start the Venn diagram and see where we go from there. So here's our Venn diagram. If you like the book, then you'll love the movie, right? Just like before, it's always P inside Q. Now, what was the second statement? The second statement was, you did not like the book. So if we come here, you did not like the book just means you're outside this circle. But again, we could be in the blue stuff or we could be out here, so it lands on the border and therefore invalid. It's that simple. Okay, how about this one? A narcotic is habit forming. Aspirin is not habit forming. Conclusion, aspirin is not a narcotic. So we're going to identify P is going to be a substance is narcotic, and Q is going to be the substance is habit forming, and we're going to draw our Venn diagram based on that. So a narcotic is habit forming. So here it is. Habit-forming substances has a subset of narcotics, right? There are other habit-forming substances, like nicotine and things like that, alcohol, and then narcotics are a subset of those things. So here's our kind of if-then statement. And then it says aspirin is not habit-forming, so it has to go outside the blue circle. So there's our X for aspirin, and therefore aspirin is not a narcotic, which is true, right? So it's a valid argument. It can't be in this thing, so it's a valid argument. Again, it's not because aspirin is not a narcotic that that makes it valid. It's the fact that the setup says that it can't basically be in that circle. Okay, whether or not aspirin was a narcotic doesn't matter. Like, let's say there was a narcotic out there that wasn't habit forming. Obviously, you'd say so-and-so is not habit forming, but it was a narcotic, right? And then that would be a problem. There is no such a thing, because this is actually one of those arguments that is true, but you get the idea that the truth of it doesn't matter. It's just whether or not the X can land in a specific place or on a border, right? So whether or not it holds up with the structure of the argument or not. That's what's valid or invalid. Okay, deductive arguments with a chain of conditionals. Another common type of deductive argument involves a chain of 3 or more conditionals, and such arguments have the following form. We have an if P then Q, then we have an if Q then R, and our conclusion is if P then R. It's kind of the old transitive theory of mathematics, right? If A equals B and B equals C, then we know A equals C. That's an actual true deductive argument. These aren't necessarily always going to be true, but they're going to be valid if you can use this structure. So here's a typical example. So if elected to the school board, Maria Lopez will force the school district to raise academic standards, which will benefit my children's education. Therefore, my children will benefit if Maria Lopez is elected. So basically they're saying if she's elected, she'll raise academic standards. Academic standards being raised will benefit my children. Therefore, if she's elected, it'll benefit my children. You see how we kind of turn those into 3 if-then statements? So here they are. And if we put them all into their statements of P to Q and Q to R, we can see that the argument is valid. Okay, so in conclusion, perhaps more than any other subject, mathematics relies on the idea of a proof. And a mathematical proof is a deductive argument that demonstrates the truth of a certain claim. Sometimes we call this a theorem. And a theorem is considered proven if it's supported by a valid and sound proof. Now, although there are mathematical proofs some use deduction, theorems are often discovered by induction. So we can test the following rule. For all numbers A and B, A times B equals B times A. We'll begin with some test cases and see that it works, right? We'll throw in a bunch of things and go, yeah, they all work, okay. So then we would have to generalize it. These 3 test cases are each somewhat different, mixing fractions, decimals, negatives, so on and so forth, yet the rules work in all 3 cases. This outcome offers a strong inductive argument in favor of the rule. Remember, inductive is you use specific cases to then generalize to the general rule. So although we've not proven the rule, we have good reason to believe that it's true. And our beliefs would be strengthened by additional test cases that confirm the rule. And the nice thing about this kind of inductive reasoning in mathematics is if you can just find one case where it doesn't work, you've disproven the rule. So it's really easy to disprove a rule this way. It's really hard to prove a rule this way. All right, that's it, guys. Hope that helps.